Welcome to the First Principles video and blog series. My name is Pradeep Vincent. I'm the Senior Vice President, Chief Technical Architect for OCI. At OCI, we strive to innovate on behalf of customers, both in terms of functionality, features, services, as well as performance and durability and resiliency. For our storage services, which are really the bedrock services of OCI, customers rely on it to store business-critical data. They use it for backups. They count on the storage not to lose data. So durability is absolutely important for OCI storage services. So today we're going to talk, about some of the architectural aspects about how we actually achieve our durability in some of our key OCI services. To talk about this, here we have Laurion.
Hello.
Who's our architect in OCI Object Storage Service. Welcome, Laurion.
Hi, Pradeep.
Tell us a little bit about how we actually go about achieving durability.
In object storage, I'd say durability, and you touched on this already, has three critical prongs to the approach. Number one, you need to store data redundantly, which might mean replication, but might not, and we can discuss that in a bit. But you have redundant data, so that if you lose a disk, if you lose a bit of data, you can still restore everything you originally stored. Secondly, especially at scale, you want to restore your redundant data in a way where you don't have correlated failures. You don't want to put your redundant data, say, on two disks in the same machine. You don't even want to put it on two machines in the same rack. You want to spread your redundancy across fault domains. And the last thing is, when you do have a hardware failure, which are inevitable, especially at scale, you want to recover from your hardware failure as quickly as possible. And that means automatically detecting the failure, automatically recovering from the failure, and you're doing that with online spare capacity so that no hands-on work is required to recover from a hardware failure.
Got it. So essentially, talk about replication and perhaps other techniques beyond replication. Spread that across multiple hard drives or SSDs, across multiple nodes, across multiple racks, across multiple data centers, and then have a really automated way to recover from failures.
Yes.
So let's actually talk about how we actually replicate.
There are two main ways of getting redundancy in the system. You can simply store multiple copies of the data. And a classic example of this would be a RAID 1 system, where you put maybe two drives in a machine and the second drive is a complete bit-for-bit copy of the first. The challenge with this is it rapidly becomes very expensive, because in order to obtain extremely high durability, you need more than two copies. The general rule in object storage is you want a level of redundancy such that it takes at least 3 concurrent disk failures before there's any risk of data loss to an object. And typically we're storing data in a way that requires 5 or more concurrent disk failures. So once you start doing that, you realize you don't want to store a lot of copies of your data because it drives your costs up immensely. And so you start talking about systems that use erasure coding. And erasure coding, you'll see it in systems like RAID 5 or RAID 6. But the central idea is you take in some data, you take in your original data, and you break it into chunks. You break it, in this example, into 6 chunks such that you can reconstruct the full data from any 4 of the chunks. So here we've taken a sample string, produced 6 sample chunks. They're all going to be about the same size. And mathematically, from any 4 of these, you construct all of the original data. This has a property that if you take these chunks of data, all 6 of them, and store them on 6 separate drives, you require at least 3 of the drives to fail before this particular sample data becomes unrecoverable. So you've achieved the level of redundancy that you would have if you did, say, 4-way mirroring, but the stretch factor is only 1.5. So you could store, say, a terabyte of data.
What is the stretch factor?
The stretch factor is if you store a terabyte of logical data, of customer data, how much space does it actually consume on your disks? And here with a stretch factor of 1.5, storing a terabyte of customer data uses 1.5 terabytes of disk, which makes it quite cost efficient. If you stored 4 copies of your data, which would also have the same durability, it would also survive, or it would survive 3 hard drive failures, you'd be using 4 times as much disk space. Or if you stored 3 copies, you would have to use 3 times as much disk space, making it twice as expensive to buy your hard drive storage.
Got it. So essentially, erasure coding gives you the benefits of, n-way mirroring, if you will, 4-way mirroring or whatever, but at the same time in a much more cost-efficient fashion.
Yes.
So that we can pass on the benefit to our customers.
Yes. If you're storing exabytes of customer data, you need a cost-efficient way of encoding it that also meets your durability, performance, and availability goals.
Got it. Well, so do we just use erasure coding everywhere, or are there scenarios where we actually need to use, replication?
It actually depends on the object size. So this example is not a good example for erasure coding, because we've taken a very small amount of data, we've broken it into 6 chunks, but now in order to retrieve the data, you have to go and retrieve 4 chunks from 4 separate disks on 4 separate machines. That's really inefficient to read, it's really inefficient to write. So you find that once you have small amounts of data, it's actually better to just replicate the data across multiple disks. The total disk space is small because most of the data in the system is in large objects, and the durability is high, and it performs well. So we switch between erasure coding and replication depending on object size right now. And you can even switch between different erasure coding schemes depending on the exact use case you have.
Got it. So what I heard was for small objects, perhaps, this being an object, well, we're probably not going to actually use erasure coding because these little bits or bytes, if you will, are pretty small.
Yes.
So retrieving them and handling them has sufficient overhead. You really don't want to do that. So for small objects or chunks, if you will, we just do replication.
Yeah.
And for larger ones, we do erasure coding. And moreover, we actually do different types of erasure coding for different sizes. So let's actually talk a little bit more about that. So I'm looking at this, N and K. I can imagine N being high, K being higher than this. I can imagine this being 24, this being 16. I can imagine different ratios. How do we actually go about deciding these magic numbers, if you will?
The stretch factor is driven by performance concerns. As you make your stripe wider, you become more vulnerable to high tail-end latencies, for example. If you, at an extreme, split an object into 50 chunks, we had to read any 40 of them to reconstruct the object, you have to do 40 IOs to 40 separate servers to 40 separate disks. And your latency is going to be the latency of the slowest server, of the slowest disk out of the 40, and that makes your tail-end latencies high without saving you necessarily a ton of disk space. The other driving factor for us is the availability for reads. If you drop your stretch factor below 1.5, whatever that means, you have 9 chunks, you need at least 6. Say you say, I'm going to have 9 chunks, I need at least 7. Now, if you lose a fault domain or an availability domain in a region that's got 3 of them, which is our normal configuration, you lose the ability to read that data until the problem is fixed, the network problem or the power problem is fixed. So to maintain our availability SLA, we want to keep the stretch factor at least 1.5. And to stop fighting against super high tail latencies, we want to keep the number of stripes not excessive, not 100, not 50, but you typically see things in the industry in teens or the 20s.
Got it. So what I heard about this is a more complex, calculation and formula and consideration that includes, cost, performance, availability, and durability.
Yes.
All of that. And I think what I heard was, the stretch factor, what we have found is that, the floor of it really has to be 1.5 in order to, deliver good performance and availability.
Yes.
Right? Maybe not for durability, but like for the other aspects. And then, we kind of want to increase N and K as much as possible, except that when you increase it after a point, it's going to start impacting, tail latencies
Yes.
and performance and the overhead. So it's a, trade-off in terms of, the performance and the overhead associated with that and achieving high durability, right? Cool. Well, that's awesome. So we essentially have, to summarize, we have our replication system for small objects essentially use flat out replication. We do n-way replication. And then for larger objects, we use erasure coding. And the exact type of erasure coding, differs by the size of the object. And it is a complex trade-off across multiple dimensions.
Yes.
And we essentially deal with that. Cool. Awesome. So that's about replication. Well, let's imagine something fails in here. How do we deal with that?
This is a very exciting topic because, or at least for me, when you model durability, the inputs are how often do disks fail? And industry-wide, magnetic disks fail 1 to 3% annual failure rate per year. So we expect to lose 1 to 3% of our disks per year. But in the largest region, you're going to see a disk failing an hour. So disk failures are an expected event with multiple disks failing per day per region. If you take the RAID 1 approach of duplicating drives, so I've got a drive here and this drive is a complete copy of it, recovering from drive failure takes an incredibly long time because you're going out and you're buying, say, 24 terabyte drives now, but although drive capacities increase over time, their read throughput for magnetic disks has not gone up that much over the years. So you might buy a 24 terabyte drive that can read 200 megabytes per second, and it turns out that cloning that drive is going to take close to a day. And the problem is, in your durability model, a very critical factor is how long does it take to recover from a disk failure? Because remember, we stored the data, so you require at least, normally more, but at least 3 concurrent disk failures to avoid losing any data. So in your mathematical modeling, you're trying to answer the question, what is the chance of 3 disks failing in the time window it takes to recover from the first failure? So driving down the time to recover from a failure has a massive, results in a massive improvement in your data durability. In order to do that, you have to lay out the data differently. You cannot simply clone drives onto each other. And the way we approach it is, and again, this is a simplified example that shows 3-way replication. If you discuss erasure coding or replication with more than 3 ways, the diagram is too complicated. But this simplified 3-way replication example, you break a disk, say your disk in data center 1, is separated into logical extents. And each extent is mirrored. Again, we have to keep that data separate. So we mirror it to a different disk in a different server in a different data center. And the extents are mirrored to different disks across the region. So you can see the disk in the top left, extent A has gone to data center 2. Extent B is also replicated to data center 2, but a different disk in a different machine. And you separate your mirrored data this way. The reason that this is useful becomes apparent when you talk about what happens when a drive dies. So when a drive dies, there's no impact on durability. You've still got 2 copies of all of the data in this example. The data are in different data centers. You're not worried about correlated failures or anything like that. But in order to preserve long-term durability, you have to restore your redundancy. This has to be done automatically and quickly. And the way that works is you want your new redundant copies to be in the same data center. So you allocate new extents representing the data that was on the failed disk. And those extents are allocated, again, on different disks inside of the data center. And they're empty. They don't have any copies of the data. And the advantage of doing this becomes apparent when you say, what happens when I want to restore my redundancy? We perform a lot of copies for each extent, but the copies are now between different disks in different servers across your entire region. And these extents are quite small. You keep the extents down to dozens of gigabytes or hundreds of gigabytes maybe. So copying each extent is very quick, and you copy all of these extents in parallel. Again, in this simplified example, you've only got 4 extents. But you can see by copying the data across 4 different servers and 4 different disks, you're going 4 times faster. And in production, obviously, you have hundreds or thousands of extents per machine. These copies all run in parallel. They fill up the extents, and now you've restored all of your redundancy. What we find in production is that the total time to recover from a disk failure, this is time to detect the failure, allocate the new extents, trigger the copy, and wait for the copy to finish. That entire end-to-end time is under 30 minutes. And so when you do your modeling of how durable is the system, you're like, what mathematically are the chances of at least 3 drives failing within a 30-minute window? And typically with erasure coding, you're restored in a way you require 4 or 5 failures. The chance of that happening is so small that you easily exceed the 11.9's durability that object storage is targeting.
Yep, got it. So to summarize, the first thing, we actually distribute the replicated drives, if you will, across multiple data centers or fault domains or ADs. And then for every disk drive or a physical drive, if you will, the data is actually split into extents, and each extent is actually replicated to different drives on different machines in different data centers, so that when that fails, the recovery process is really a distributed recovery process.
Yes.
Where all the machines across multiple data centers kick in all at the same time to recover this single failure super fast, so that we really close down the window of recovery, because the time to recover is essentially, the key to achieving high durability. So that, we minimize that, we minimize the probability of any other failure happening during that window.
Yes.
Got it.
We did a lot of math around that in the initial design phase of object storage, and minimizing that recovery time is what gives you incredibly high durability.
Got it. So that's essentially the magic behind achieving 11 nines durability that we promise for our object store. Awesome. Well, so, one of the things that occurs to me, and it's always been true in cloud industry or any other software industry, no matter what we do at the architecture level, software engineers can actually destroy all of that and overcome all of that using a simple software bug that's deployed everywhere. And then it takes down a whole bunch of machines and, deletes data. No matter what the architecture, we can actually lose data. So what do we do to actually really minimize and eliminate the probability of software bugs, if you will, taking down the durability?
So it sounds simple. There's just two things you do. Test the software extensively and roll it out slowly. Both of those are hard to do in practice, and they become part of your engineering DNA in a way. When you look at testing the software, you go all the way from formal verification, which OCI does quite a bit of, to pre-production testing. Very extensive pre-production testing on your different hardware fleets, including simulating failures and recovering from them, to constantly testing in production to make sure that your test data is retrievable. You do data scrubbing, where you just read data back off of disk to make sure it's okay. And then when you worry about bugs being released everywhere, you roll out your changes relatively slowly. You don't deploy to all of the regions at the same time. You don't deploy to all of the machines in the region at the same time. You don't even deploy to all of the machines in a data center or a fault domain at the same time. You roll them out slowly, you monitor how they perform, you test constantly prior to release, during release, and after release. And that means that if you did have a software bug, you would catch it early or catch it before it had large impact on anything.
Got it. So essentially, to summarize, it really goes to the core of engineering culture that we have in these service teams, where it really focuses on, there's a lot more focus on, testing before any deployment is done, significant amount of test investment. And then when we do deployment of new software or, new functionality, there's a very slow, methodical, careful cadence to deploy software across the fleet. We, roll it out to a few nodes, test it, and then roll it out to more, maybe to one fault domain, and then wait, see how it does. Is there any impact? And the reason for that is, a single fault domain failing cannot take down, or lose data.
Yes.
Right. But on the other hand, if a code is deployed everywhere, it's going to lose data. So we, roll much slower to see how things go, and then go forward. But like everything in life, all of this must come with some trade-offs. I'm pretty sure all the time that we are doing for extensive testing, we could have used for some fancy features. Why are we not doing that?
Object storage is at the bottom of the cloud. This is the infrastructure level. Broadly, customers come to object storage to store their data and read it back and have it always be available and durable at a low price. And those are the core priorities when you look at what customers want, when you look at what we have to deliver. And so that emphasis comes above everything else.
Got it. So we are not like a video game company.
No.
We are like a core infrastructure group that really focuses on creating a hardcore bedrock that everyone can rely on.
There's no feature worth shipping that would in any way jeopardize durability.
Yep, got it. Cool. Well, thank you for joining us, Laurion,
Thank you very much.
Well, thank you everyone for watching this.